welcome you all to this course on electron diffraction and imaging. Okay. In today's class, we will discuss various lens aberrations and its effect on the resolution of the microscope. Okay. The first question which arises is that why do we use lenses? Because we know that we use lenses to magnify objects. Why do we have to magnify objects? Because our eye has got a limit on the extent to which the objects can be resolved. If we wanted to see features which are smaller than the resolution power of the eye, then we have to magnify the image. What is the need for magnifying the image? The reason essentially is that though the light, if we use, for example, if we use a light as a probe, then what is going to happen is that the ultimate resolution is given by the wavelength of the radiation lambda. Okay. So that means that in the case of light, generally it is about something like 500 nanometers is going to be the wavelength of the radiation. That means that the features which are of the order of 500 nanometers is resolved whenever light falls on the material. Okay. Even in this room, if you look at it, when this light is falling onto this table, the features of this order are essentially resolved, but our eye is not able to see it, because the resolving power of our eye is about something like roughly 0.1 millimeter. To overcome this, we have to magnify that features so that the separation between them becomes greater than the resolving power of the eye. That is why we require a lens to magnify it. But when we use a lens, okay, especially what are the features which we look for the lens, what are the characteristics which the lens should have? One of the characteristics of the lens is that it should do a faithful reproduction. What is the reality of the system? The simplest case which we can take of is a magnifying lens which we normally use when we can't read objects properly. But this is an example which is being given here. With a lens we are trying to magnify objects. This side you can see the normal image, and here it is the magnified image which we can see. But if we look at it, we can immediately make out that the image is curved, it is not in a straight line. Okay. The magnification appears to be different from edge to the center, and the center it is focused well, for example in this case, and the edge it is out of focus. All these problems occur because a simple lens which we use it to magnify has got a lot of aberrations which are associated with it. Because of this aberration, we are not able to get a faithful reproduction of the object in the image. In fact, one point which I want to quote at this, the statements which have been made by Maxwell in 1858. He has talked about what is the properties of an ideal image. One, each point in the object, okay, there should be an equivalent point in the image. When we form an image using a microscope, it could be a optical microscope or it could be a electron microscope. And then when we have an object, okay, this is what essentially is given here. This is an for example, here if you consider a point object along the optic axis, for an ideal lens a point image should be formed, the image. So if the resolving power of the lens, like for example in the case of an electron microscope which is operating it at 200 keV, the wavelength of the radiation lambda is of the order of 0.0025 nanometer. That means this is the limit of resolution. So for an ideal lens, all the atoms in the crystal should be resolved, but that is not what it happens. This is because of various lens aberrations which are associated with the lens, which we will come to shortly. The next point which he wants to which he has mentioned is that the object and the image are geometrically similar. Okay. What does it mean? That is, if object has got a particular shape, the same shape should be reproduced in the image as well. And the third is, if the object is planar and perpendicular to the optic axis, so is the image. These 2 points are shown in this slide. Here if you see it, this is ABC is an object, this is a lens system which magnifies it. Okay. We are able to get a magnified image on the screen. If we measure the ratio between AB here and AB here, BC here and BC here, okay, and also the angle between them, they are faithfully maintained, then only we can say that this is a true reproduction of the image. But what normally happens in many of the lenses, one, for an example which is shown here is a square grid is taken as the object, and you find that the grid itself is distorted. This is the way it appears. When this appears, we call it the Pincushal distortion. And this is another way in which a square grid can appear, then we call this a barrel distortion. Here there is a rotation is also associated with it, then it is called as a spiral distortion. Then there is another distortion which can come, is that the image is not formed perpendicular to the optic axis for an object which is there, like in this case for a plano-convex lens, you can see that that image is formed in a curved space. Okay. So, this is also another type of an aberration. So, we have seen curvature, then different types of distortions, and there is another aberration which comes because of the curvature of the lens, the spherical lens. This aberration is normally called as the spherical aberration. Before we go into understand the aberration, okay, what we should know is that why does these aberrations arise in the lens in the first place. In 10th or 11th standard, everybody has studied about geometrical optics, and in this we consider that if a lens is there and if we have an object which is kept along that optic axis, and then we know that the rays which are parallel to optic axis go through the focus, and the ray which passes through the center of the lens, the place where they meet, this is where the image comes. This is the object, this is the image. If this distance is u and this distance is v, and if it is f, we know 1 by u plus 1 by v equals 1 by f. This is the formula which we use to construct that image. But what one should understand is that when this image is being constructed, okay, there is one condition which is there. We call that the rays are paraxial rays. What does paraxial rays mean? When the light from the one medium which is air enters into the lens, okay, since the refractive index is different, it has to obey the lens law, the Snell's law. Okay. What is Snell's law? Snell's law says that sin theta by sin phi equals mu, the refractive index. That is, if this is the normal, this is theta and this angle is phi. Okay. This Snell's law has to be obeyed, and this is the rule which governs how the rays are bent when it enters from one medium to another medium. If we apply this rule, okay, then what essentially will happen will, for an ray from an object, okay, which is parallel to optic axis but not very close to it, will it obey this rule or not? Okay. This law, this formula itself, this Gaussian formula itself is derived, okay, for the condition that these are all paraxial rays. What are paraxial rays? Paraxial rays are the rays for which this value of the theta and phi becomes so small that this mu can be written as theta by phi. That is, sin theta can be approximated to theta and sin phi can be approximated to phi. But what is normally happening is that the actual expansion for sin theta is sin theta equals theta minus theta cubed by 3 factorial plus theta to the power of 5 by 5 factorial minus theta to the power of 7 by 7 factorial. This is the way the sin theta has to be expanded. So, only when the value of theta is very small that higher order terms can be neglected and sin theta can be approximated. That means that for rays which are very close to the optic axis only this rule is valid and this Gaussian formula is valid. But that is not the case when the rays are coming falling on the lens on all points. In such a case we have to use this formula, or the approximation which we can use it is, this is the approximation sin theta can be, if we use this approximation which is closest to the reality, then what is going to happen is that the rays which are coming closer to the optic axis, they form image at one particular point. The ray which is coming at the edge of the lens, they are focused to a point. In all the cases the Snell's law has been used to trace the ray which emanates from the object and forms an image. So, now we can make out that the ray which is farther away from the optic axis, they form an image on the Gaussian plane. This plane where the image is formed for paraxial rays, this is called as the Gaussian plane. In this the image size is very large. Here that image size is again. So, in between there is a region where that image size is minimum. This is called as the disk of least confusion, which you have all studied. So, this same ray tracing itself, we can look at it in a different way. Instead of a ray, if we consider the light as a wave which is propagating, then we can think of from the object, from a particular point in that object on that optic axis, the spherical waves are emanating, and these waves one can make out that they come and meet at that lens. What does that lens do? The lens essentially gives a phase shift, so that the crust has been changed to this particular shape, and when this propagates in this direction, it will come back to a focus at a particular point which is the image point. So, here it is only an advancing the phase shift which is doing it, which is varying as we go away from the optic axis. In the case of a convex lens, if we consider it, here what is going to happen, it is essentially delaying that phase which is happening. So, in this case also for a point object, we are able to form a point image, and these lenses are considered as ideal lenses. Why I am mentioning this point is that later when we talk about high resolution microscopy, we have to consider lens as phase shifters. Let us come back to the spherical aberration. What is spherical aberration? The spherical aberration is nothing but when we try to draw the ray diagram for a lens. If we use the case of paraxial ray, this is the formula which we will be using to find out the position of that object and the position of that image. But when the lens has a finite dimension and the angle which it submits, the ray submits with the lens surface is not very small, in such cases we have to use this particular formula, and if we use that, then it gives rise to a situation where the lens has different focal lengths depending upon which point the ray is entering the lens. At what, or that is at what distance from the center of the lens the ray is entering the lens. This spherical aberration, what is its effect, which we can calculate it, because what we find here is that it is not one focal length. Okay. That is for a paraxial ray, this is the focal point, and we can assume that f is the focal length, and the ray which is coming at the edge of that sample, that is focused at this particular point. So, this delta f is the variation in focal length which is occurring. This delta f can be represented in terms of some constant to the distance from the center to the edge, or there is the radius of the lens, that is to x squared plus c4 into x to the power of plus, per higher order terms it can be written. But using simple geometry, we can calculate that this x itself equals, if this distance is f1 and into tan alpha, this is that angle which it submits here is alpha, and then can be written as assuming the delta f is very small, this can be written as f tan alpha, and also the assumption that the alpha is small. Similarly, on the Gaussian plane, what is going to be the spread of that image, that Rs is equal to delta f into tan alpha. So, this is delta f into alpha. We can substitute for delta f with respect to, this is the only term which is being used first time. When we substitute this one, that value of Rs turns out to be, okay, a factor Cs into alpha to the power of 3. Okay. This is the, so that is the diameter of the image. Okay. It is going to be 2 C alpha Cs into alpha to the power of 3, and at the disk of least confusion, the diameter is going to be 0.5 Cs into alpha to the power of 3. Okay. So, for a point object, we can make out that it is not a point image, there is a disk of least confusion is what we get it. This is one aberration. Okay. This aberration itself, we have just shown it for a point object which is going there on the optic axis, and we do not get a point image, but it is an image which is spread out in space. This, if we consider it as waves which are emanating from the sample, okay, and then propagating, then we can make out that the rays which are away from the optic axis, they are bent. Okay. The crust has been bent a little bit more forward, because of that only this sort of an aberration which is occurring. So, so far we have considered a spherical aberration for a point object which is lying on the optic axis, but normally object have a finite size like in this example. So, the rays which are coming away from the optic axis from this point on the sample, what will happen to it? Okay. This also leads to an error or an aberration, and this aberration is called as the coma. It is like a comet, the shape of the aberration looks like that of a comet. Here one can make out that the ray which is passing through the center of the lens, that goes undeviated. Okay. And for this particular ray and the rays which are close to it, paraxial rays, okay, the focal point is here. So, it is a small point at which we form that image, and the rays which are far away, there is going to be a spread, and that is what essentially is being shown. From here to here as we go, the size of the image itself is becoming large. So, this is like that of a comet which you can see, this is that shape. Okay. This aberration also has to be, so these are all the two aberrations of the microscope, okay, and this is also related to the spherical aberration coefficient Cs. Okay. What is the other aberration which arises in a microscope? This is called as the astigmatism. That is, if the lens itself is not perfectly spherical, the surface is not spherical, we find that there are some distortions, okay, then this will give rise to two different focal points in two perpendicular directions. That is, if a ray enters that lens in this one and the ray enters in this direction, it will be focused at two different points. This gives rise to not a sharp image, but an image which is distorted. How this can be corrected? This can be corrected by putting in front of this lens a non-cylindrical lenses. That non-cylindrical lens essentially is a lens like this one, another is in a perpendicular lens like this. These sort of lenses, if we use that, we can use them to compensate and correct the astigmatism. Okay. How is it done in a transmission electron microscope? Because in an electron microscope we assume, or in all microscope we assume that lenses which are being used, okay, and in an optical microscope is the one which we are taking it as an example and talking about all the lens aberrations. I will come to it later and mention to you that all the lenses in a electron microscope, all the, whether it is electromagnetic or electrostatic lenses, these are all convex lenses are the ones which form, and no concave lens can be formed, the electromagnetic lens. Because of this, the lens aberration, especially the spherical aberration and comma, is going to be there. Similarly, depending upon the design of the lenses, how the lenses are machined and formed, okay, the astigmatism can come. So, how this astigmatism is corrected in the case is using what is called as a stigmator. Stigmator is nothing but in a plane here, because Z is the direction in which the ray is passing through. We have some plates or rods are there to which a positive and a negative voltage is being applied. Okay. So, this will generate essentially a field like this. Okay. These fields, what it is going to be, the rays which are away from the optic axis, only those rays will be affected, and the rays which are passing close to the optic axis or along the optic axis, they are not going to be disturbed. So, this is with an electric field we can generate a stigmator, or we can keep magnets also like this. Here some magnets are there, the north pole in these two sides and south pole. Here again this is how the field lines will be moving. So, because of these field lines, okay, only the peripheral rays will be affected. By controlling the strength of this magnetic field, we can correct for the astigmatism of the lens. Okay. And what is the error which comes due to for a point object, essentially because of the astigmatism, it turns out to be beta is into delta f. What is beta is that if this is the lens size, okay, and this is the diameter, and if you keep an object at the center, what is the maximum angle which submits with the lens? This is what is called as the angle beta. The other one, as I mentioned, the curvature of the field. What is the curvature of that field for a lens which is like a planar convex lens? For an object which is perpendicular to lying perpendicular to the optic axis, one can see that the rays which are along the optic axis, the image is formed at this particular point obeying the paraxial ray condition or the Gaussian formula, and the ray which are far away from it, the image is formed at a point which is in front of the Gaussian plane. So, because of that, there is a curvature of this field. How this can be corrected? This can be corrected by using a lens which is essentially a planar convex. If you use it, this will be deviating these rays a little bit so that they will be focused at the this way we can correct the curvature of the lens. What are the other aberrations which are there? As I mentioned, that is because of variation in magnification across the image field, that is a pincushion, barrel distortion, spiral distortion. These are all the other aberrations which a lens will have. So, essentially if you look at it, what we have talked about is for any lens there are 5 aberrations which are associated with it. What are those aberrations? Spherical aberration 1, comma is another, astigmatism is the third, curvature of the field is the other aberration, distortion is the 5th aberration. Okay. When we want to compensate for the aberrations, we have to correct each of these aberrations and make it 0. This is what this if you go into the theory of lens aberrations, they use what is called as the Siddal terms. These terms have to be independently made equal to 0. That means that every aberration has to be, that is, we cannot use one aberration to correct for the another, so that at a particular point it looks like as if the aberration is corrected in some region. Each of the aberration has to be independently corrected. That is what it means. These are all the aberrations which are connected with a lens. In addition to it, there is another aberration which comes, okay. That aberration which is called as a chromatic aberration, okay. This also you might have studied, but for the sake of completeness I wanted to mention that this is also one of the important aberration which has to be corrected. That is, this aberration arises not because of any problem with the lens. This aberration comes because of non-monochromaticity of the wavelength of the radiation. That is, the wavelength lambda, when we talk about it, this value is not a particular value, there is some line width which is associated with it. When there is a width which is associated with the radiation, okay, as I mentioned earlier, the lens acts as a phase shift, okay. That means that depending upon the thickness of the lens and the wavelength of the radiation, okay, that is the phase shift which it introduces is the refractive index into T, the thickness, okay. So, depending upon different medium, the same even if the wavelength depending upon different wavelength, the phase shift which it introduces is going to change, okay. That is what essentially is the reason for chromatic aberration, okay. In the case of a light radiation, it is essentially the spread is arising because of the finite width of the monochromatic source. In the case of an electromagnetic radiation, okay, how do we produce monochromatic electrons, okay. There are many ways which are done. One is thermal ionization is used to produce electrons. 2 or cold or hot field emission. That is, in thermal ionization what is being done is that the filament is taken, it is raised to a very high temperature so that the electrons are emitted. When the electrons are coming out of the sample, they have a finite spread and these electrons are accelerated to some particular energy, okay. So, this spread inherently in the electron energy initially, that itself gives rise to a spread in the overall total energy, and that will be reflected in the wavelength of the radiation. Similarly, the voltage which we use, high voltage which we are, this is also generated from converting an DC into an AC. In this case also there are some ripples which are associated with it, and that can also give rise to some fluctuations in the voltage. The third point which happens is inelastic scattering. That is, as the light radiation passes through the sample, it interacts with the material, and sometimes some energy of the radiation is lost as it passes through the sample. This gives rise to electrons with different energy which is coming out of the sample surface, okay. So, that means that when the beam which is initially entering is monochromatic, but the beam which comes out, okay, there is a spread has increased in that energy, and this also will give rise to chromatic aberration. So, here also what we can make out is that since the phase shift is going to be different for the rays which are having different wavelength, we will find that depending upon that energy, okay, either they can be focused at this particular point or they can be focused at this particular point, and this finally gives rise to, as in the case of a spherical aberration, this gives rise to disk of least confusion which is coming. So, the diameter of this disk of least confusion is related to beta, the angle which it submits with that lens, okay, multiplied by delta f, okay, and this delta f depends upon the spherical aberration coefficient Cc of the lens into delta E by E, the energy spread, okay. For a weak lens, that Cc is f, and for a strong lens, the CC is f by 2. Okay. How is this chromatic aberration corrected? In the case of an optical microscope, we can use lenses with different refractive index, a combination of them. Okay. They are called as achromatic lenses, with which for some particular range of wavelength the chromatic aberration could be corrected. Electrons, the only way we can do it is that we can make the power supplies, okay, the fluctuation in the voltages are so small, okay, and so that it is a highly stable supply. The thermal spread, essentially we can reduce it by going for a field machine gun, okay, and then we can make the sample as thin as possible, so that the influence of inelastic scattering on the chromatic aberration could be reduced. Another is the lenses which we use are electromagnetic lenses, where we apply current. By changing the current, the focal length of the lens itself changes, okay. By making the lens supply, the power supply highly stable, we can bring about reduction in chromatic aberration. These are all the ways the chromatic aberration is corrected. So, essentially any microscope, if you look at it, okay, the aberration comes one from the lens which we are using it, the other aberration comes from, like a chromatic aberration, which comes from the source of the radiation itself, whether the radiation is highly monochromatic or not. Both these facts together decide all the aberrations which are going to be there. All these aberrations can affect the resolution of the instrument. This is what we will discuss it shortly, how these various aberrations affect the resolution. Before we go into it, let us look at how this resolution itself is defined. Okay. We know that if we have a screen on which there is a hole is going to be there is a light source from which the light is coming. This will be forming on the screen the image of this hole. Okay. If we make the size of this hole small and small, and the size becomes nearer to that of the wavelength of the radiation which we are using it, then what happens is that normally it has been observed that you do not see a sharp image. There are some rings could be seen, okay, beyond the geometrical image. Okay. This is called as an airy disk. Okay. So, this has been observed long time back itself, when people had been observing it at stars. Okay. So, essentially what we can make out is that at the center there is a maximum intensity. Okay. Here the same thing which is shown with respect to a telescope which is being used. This is a lens which in front of it, at the center maximum intensity, and the first minimum intensity occurs at a particular point. Okay. The separation between this x, okay, that is what essentially turns out to be this angle alpha which this submits, this turns out to be is equal to lambda by d. These derivations one can, from the geometry one can work out. Okay. So, essentially what is going to happen, this x by 2 equals, this is the sort of a formula which takes place. This formula is that for us, if we use a spherical aperture, because the lens itself can be considered as a spherical aperture, and in that case that Bessel function has to be used, then this factor alpha, the angle which it submits, this turns out to be 1.22 lambda by d, okay, where d is the diameter of the aperture. So, if this diffraction limited for what we have considered earlier is for a one point source, what is the sort of an image which is formed? The image itself we can make out that there is a central disk and there is a varying intensity which comes. So, some rings could be seen outside. Suppose we have two incoherent sources, one and another source which is close by, okay. Then depending upon the separation between them, it can so happen that the airy disk corresponding to one of them, okay, and the area corresponding then quite far away, they can be seen separately. But what is the minimum separation at which they could be seen? This is a criterion which has been put forward by Rayleigh, and this criterion essentially is that if 2 point sources are regarded as just resolved, okay, when the principal diffraction maximum of one image coincides with the first minimum of the other, okay, then using this geometry one can derive it, and then the formula what we get it is that the separation between that objects if is equal to 0.61 lambda by theta, okay, where theta is the angle, or earlier we have used the term beta to represent it, by beta that represents the limit of resolution. So, this is the best image which we can achieve, okay, when we use a lens or when we use an aperture, okay. And in the case of an optical microscope, here we use another term, the denominator n, which we call it as the numerical aperture. Here what I had shown it is that the same, when only one object which is considered, okay, there is one light source which is being considered, which is an incoherent source, then this is the way that image appears for a aperture whose size is of the same order as the wavelength of the radiation or close to it. And when the separation between them is very large, this is how both the sources will give rise to individual images, and we can resolve them very clearly at some particular distance, okay, where the minimum of the one matches with the maximum of the other, they are just resolved, and in this case our eye will not be able to resolve it. So, this is what essentially the images which are being shown corresponding to these three cases. Here we can see the images which are resolved, here it is just resolved, here it is very difficult to make out this is one image or a two image, okay. So, this is the criterion which has been put forward by Rayleigh to say that this is the resolution of an equipment. Now, having considered this Rayleigh's criterion, let us now look at what is the effect of spherical aberration on the resolution. What does the spherical aberration do for a point object? Okay, we do not get a point image, we get a disk of least confusion, okay, or in the Gaussian image plane, this this is going to be the twice the diameter of instead of a point image, we get a disk with a diameter, okay. Suppose we have the same, we can consider two sources are there, point sources are separated by a distance which is larger than this. If they are there, each one of them will give rise to a disk of least confusion, or on the Gaussian plane we will be getting a disk, we will be getting it, okay. If they are well separated, we will be able to see them as two different objects, okay. Now, for some particular distance, and this will be actually a magnified image which we get it, and here for some particular separation, that is the disk starts overlapping, and then we find that only for some particular separation between these objects, we are able to see them as separate one. That means that the resolution now compared to Rayleigh criterion, the lens aberration as such is, since it is increasing the for a point object, it is not giving a point image, okay, there is a spread, the resolution is becoming poorer and poorer, okay. The objects which are separated by larger distance only could be seen very clearly because of the spherical aberration. The same thing happens with a chromatic aberration also, because you know that for a point object we get a disk of least confusion, okay. At some particular separation between them, the overlap is such that still we are able to resolve them as two individual ones, okay. So, far we have considered with respect to lens aberrations, both spherical aberration and chromatic aberration, how it is affecting the resolution, okay. Now, if we take a light source itself, okay, if the light source is thermionic source, then what is going to happen? The electron emission is taking place from a finite area of that sample. So, the current density is one that matters, and this also gives rise to some practical limit on the size of the source which we can use it, Okay. The size of the source also has an effect on the resolution. So, this size of the source is given by this formula, which you can go through it, okay, and understand it. Essentially, the brighter the source, that means that it is from a point region the electrons are emitted with very high intensity, okay, then this value of D0 becomes small. That is what essentially one should understand. Finally, when we consider the resolution, we have to consider the total resolution, that is what is called as the point to point. Now, what is the spread which it is going to cause for 2 points which are separated by a finite distance? It is decided by the spherical aberration, okay, chromatic aberration, and then it is due to inherent property of the source. This is the Rayleigh criterion, and then another due to a finite size of the source itself. In this, we have just taken the square of all the terms are added, but this can be done only when we assume that all these errors are coming due to essentially a Gaussian distribution. Okay. If it is non-Gaussian for a Lorentzian, then this has to be just a linear addition. So, we know that as far as the lens is concerned, this is what essentially the spherical aberration which it comes, assuming that the beam is monochromatic, then this term can be assumed to be 0. We assume that the source is a point source, then this term also can be taken to be 0. Then these are all the two terms which are going to affect the resolution, okay. And these are all the formulas which has been derived earlier for the Rayleigh criterion for the point source, okay. If you use an aperture of or a lens of a particular size, what is the spread which is going to cause to the image, and the another is that the spherical aberration for a point source, what is the spread which is going to cause. What one should remember is that here it is 1 by beta dependence, and in this case it is beta to the power of 3 dependence, okay. If we substitute these values and then try to optimize it, we will find that the value of beta is 0.61. This is the optimum. Lambda by Cs into root 3, okay, the whole to the power of I think 1 by 4. Okay. This is the optimum angle at which we get the best resolution. And what is the best resolution which is possible? This D0 turns out to be 0.9 Cs to the power of 1 by 4 and lambda to the power of 3 by 4. Okay. So, essentially from this expression we can make out that a small variation in lambda, reduction in lambda, can bring about large difference in the resolution, that the resolution can become better, whereas for Cs there is a large variation in the spherical aberration coefficient is required. Okay. So, with this concept, in fact lot of high voltage microscopes have been constructed. Okay. In these microscopes, okay, the voltage has been increased up to present day microscopes are available where one can go up to 3 million volt energy. So, the resolution can be improved considerably. Also the when the resolution becomes high, or also when the energy becomes high, the thickness of the sample which we can, useful thickness of the sample which we can examine also increases. Both are an advantage, and but the disadvantage essentially is that when the energy increases, lot of radiation damage is produced in that sample, so that the microstructure of the sample could be altered during examination of the sample. That is one of the disadvantage microscope. This one can substitute values and calculate, but what normally happens is that here we consider the wavelength which is this order with a Cs for a normal lenses which are of the order of about 1 to 2 millimeter. Okay. spherical aberration coefficient, then the value of D turns out to be around close to around 0.2 nanometer. Essentially what it means is that the limit of resolution of the microscope is about 0.25 nanometer, but actual resolution which we can practically achieve is 100 times worse with almost all the lens aberrations which has been optimized. Present day microscopes are there where the spherical aberration can be made 0. These aspects I will talk about it at a later class. Okay. So far we have considered the various types of lens aberrations, and all these lens aberrations because of which the resolution which in principle we should be able to achieve has come down to this particular value. In an electron microscope, the magnification is such that is in a conventional optical microscope we use optical lenses, convex or concave lenses, or a combination of these lenses to achieve magnification. In the case of an electromagnetic lens, in the case of a transmission electron microscope, since electron is the beam, okay, they are affected by either electric field or a magnetic field. They can be deflected by an electric field or a magnetic field. So, both these fields could be used, okay, as lenses, okay, to magnify. But normally the present day microscope is essentially the magnetic lenses which are used, and these are nothing but like a solenoid, coils are wound around this, okay. Then this is the north, one is the north and the south pole, okay, and this is how the flux lines are going to be there. An electron beam which is parallel to the optic axis, passing through the optic axis, that will go undeflected, but the electron beam which is slightly away from the optic axis, okay, that will come under the action of the magnetic lines, and it's they will feel some different forces, okay. These forces are one is that velocity will be changed in different directions. There is going to be a field lines which are perpendicular to the plane of the lens, and the field line along the plane of the lens. We can take these components and one can find out what is going to be the trajectory. What is essentially which is going to happen is that the one which is deviated from here, it will be moving around like this, okay, in a helical path, and finally it is being focused to a point. That is, a lens, what it does is the ray which is coming from here, it will be in a helical path, it is brought. When it comes here, what one should understand that in a conventional optical microscope, the image is inverted. Here it is not an inversion, but there is a rotation which is taking place, and the rotation depends upon, rotation of the image depends upon the strength of the magnetic field. Okay. Here that how the forces on electrons, okay, as well as the magnetic flux field lines and how the velocities are affected, this is being shown. And in this particular case, one can immediately make out that if we look at it, it looks like a cylindrical geometry, like a solenoid. So, essentially a cylindrical coordinate system which is being used. Then if we use a cylindrical coordinate system, then r, theta, phi are the coordinates which are there. So, for the velocity vector as well as the flux vector, we can take these coordinates, and the force which is acting on the electron will be given by minus E into V cross B. So, this is how these calculations are done, this is what it is being plotted. So, the net effect essentially is that an electron which is deviating from here is brought back to a focus. So, this solenoid acts like a lens. So, the solenoid coil itself can be surrounded with the soft iron piece, okay, so that they capture all the field, and with that we can have lenses with different types of shapes. This is one pole piece gap which can be generated, and another is a soft iron piece which can be attached, so that we can have a pole piece with a different type of a gap, okay. And to control the current, one using a circuit which gives a stabilized power supply which has to be used, and another is that since the currents are very high, it is the lens itself are cooled with water, so that the magnetic field is highly stable. This is the formula which is used to find out the focal length of the lens. Generally, in the case of electromagnetic lenses, the focal lengths are of the order of 1 or 2 millimeters. When you know in optical lenses, the focal lengths are of the order of tens of centimeters, whereas here it is 1 or 2 millimeters. Here in this particular table, I had just given a comparison of electrostatic and electromagnetic lenses design, because instead of electromagnetic lenses, we can use an electrostatic lens also. But the advantage with an electrostatic lens is that there is no image rotation, okay, and it is lightweight and the power consumption is less, but the voltage has to be highly stable voltage is necessary, and easier is to focus ions. But the problem here, what happens is that the physical dimension of the lens turns out to be very high when that beam energy is very high. Here in this case, the magnetic lenses, it is the smaller dimension which we can use it. The aberrations can be lowered considerably, that is one advantage. Here the aberrations are high, no high voltage insulation is required, whereas for when the power supply becomes very high, okay, for high energy electrons, then the insulation and all, it becomes a massive in size, okay. And another is can be used as an immersion lens, where that the sample itself can be inserted into the lens itself. These are all the advantages. We will stop here now. Thank you.